Hi, we're going to look at 93202 Scholarship Calculus, the 2025 examination. I've already posted videos about question 1 and question 2 and all of their parts, so we're going to look today at question 3. So let's have a look at this. First part of that, A, says to prove that 1 over 1 plus sine x equals sec x times all of sec x minus tan x. The standard approach is to start with either the left-hand side or the right-hand side and see if you can manipulate it into the other side. So let's just, without further ado, do that. So we've got 1 over 1 plus sine x. And we don't want sums in the denominator here, so a way to get rid of that is if we multiply this by 1 minus sine x over 1 minus sine x, we'll get 1 minus sine squared x in the denominator, and sine squared x is the same as cosine squared x. So we've simplified the denominator to one term if we do that. So we'll get 1 minus sine x over 1 minus sine squared x. And yeah, these things are known as the Pythagorean identities. Squared in the wrong place. Got too big. So squared here. Squared here is on the sine. If you divide through this by cosine squared x, you get 1 sine over cosine is tan squared, and 1 over cosine is sec squared. And if you divide through this by sine squared x, you get cos over sine, that's cot squared x plus 1, and cosec squared x on the right. So these three are known as the Pythagorean identities, and they allow us to change from various trig functions into other trig functions with the addition or subtraction of a 1. So if I put a sine squared here onto the other side, I get 1 minus sine squared is equal to cosine squared. So that means we've got 1 minus sine x here divided by cosine squared x. And I notice straight away that 1 over cosine is secant, so we're basically almost there. If I rewrite this as 1 over cosine times 1 minus sine x over cosine, I've got secant x out the front, and then here I've got 1 over cosine. I could probably have done this a little quicker, and minus sine over cos, and that's exactly what we want. Sine over cos is tan, and that's equal to the right hand side. So sometimes we start these with the left hand side equals, and this is the right hand side. And it was asked recently whether you can do these sorts of proofs by starting with the right hand side and moving to the left. In this case, the proof, or one proof that you could do that, would be exactly the same. Just write these terms out in the opposite order. So we can go from here. We can rewrite secant as 1 over cosine. We can write secant as 1 over cosine and minus sine over cosine, and then multiply through. You'll see you've got a common denominator of cos squared x, and you'll end up with 1 minus sine on the top. We can rewrite cosine as 1 minus sine squared. We can factorize 1 minus sine squared as 1 plus sine x and 1 minus sine x, and then you could cancel the 1 minus sine x terms, and you end up with the left-hand side. So we could start one way or the other. Sometimes the proofs are easier one way than the other. Sometimes that depends on the student or the mathematician, which way they want to attack the problem with. But equals is a symmetric thing, so if you've just got equal statements, then you definitely can go either way to prove that two things are equal. This is equal to that is the same as saying this is equal to this. So you can do this whichever way makes the most sense for you. Now it says hence or otherwise, and they didn't give us very much room to do this question. Maybe they wanted us to write the problem out linearly across a line and save some space, but hence or otherwise show that this integral, or find the exact value of this integral. So this integral is going to be the same as the integral of sec x minus tan x, because we've just shown that this thing here is the same as this here. So I can replace the integrand here with what we've just shown, and it says hence do this, so that helps. So that's going to be the same as, just rewrite this a little. I can multiply this out, so I get sec squared x, and I get minus sec x tan x. And these two integrals are actually integrals that are directly off your formula book, out of the formula book. So if you integrate sec squared, you get tan x, and if you integrate sec x tan x, you get sec x. So now we've done the integration, and we're just left with substituting in the values. So one of our special triangles, 1, 2, root 3. This angle here is pi over 3, so tan pi over 3 is equal to root 3 over 1. And sec pi over 3, that's hypotenuse over adjacent, that's 2. And the tangent graph is like so. This is pi here. So 2 pi over 3 is going to be a value back. If this is pi over 3 here, 2 pi over 3 is a value back from this, so it's going to have the negative value of this. So tan 2 pi over 3 is going to be negative root 3. And similarly for sec, if we actually look at the cosine graph, sec is the reciprocal of this, but it's the same thing. But this is pi, so pi over 3 is here, 2 pi over 3 is here. The value of sec 2 pi over 3 is going to be the negative of the value of sec of pi over 3. We've determined that from a cosine graph, but as I say, cosine is the reciprocal, so secant graphs look like this somehow. But they repeat in the same sort of period. The value here on the secant is going to be the negative of the value here. So that means sec 2 pi over 3 is negative 2. And then we can work all this out. So tan 2 pi over 3 is negative root 3 minus sec 2 pi over 3 is negative 2. And then minus tan of 0 is 0. And that's minus sec of 0 is 1. So we get plus 2 plus 1 is 3, and then minus root 3 is the answer. Just do a quick double check. Yeah. I did do the same question in an alternate way with a substitution, and it's worth exploring other ways. If you can see another way to do the problem, I think I did put a substitution into this integral, but these are standard integrals, so you can just look them up. Part B. We haven't got much room for, it's only part B1. It can be shown that tan pi over 8 equals root 2 minus 1. Find a similar expression for tan 3 pi over 8. I have done this question based on my knowledge that tan pi over 4, this is another one of those special triangles where you have 1, 1 and root 2, a right angle triangle. So tan pi over 4 is 1, that's well known. And then by knowing that this is equal to 1, we can go tan 3 pi over 8 is equal to tan pi over 4 plus pi over 8. This is 2 pi over 4, this is 2 pi over 8, this is 1 pi over 8, so you get tan 3 pi over 8, and then using the tan of a sum formula to get there. We could do that without knowing this triangle, and therefore without knowing this tangent, and we just have to do the same sort of working twice to get there. So given that it just tells us this, I'm going to do it the longer way by not assuming that I know this tangent. So I'm going to basically first work out tan pi over 4, which is tan pi over 8 plus pi over 8. And when you've got the tangent of two angles, this is tan pi over 8 plus tan pi over 8, and divided by 1 minus tan pi over 8, effectively squared, because the two angles here are the same. So multiplied by tan pi over 8. That's just a straightforward application of this rule. Tan A plus B is tan A plus tan B divided by 1 minus the product of the two tangents. And then we can work that out using the information we've got, because we know tan pi over 8 is root 2 minus 1. So it's basically two lots of that. So it's two lots of root 2 minus 1 in the numerator, and in the denominator it's 1 minus root 2 minus 1. There's two lots there, but this time they're multiplied, so that's squared. So we get 2 root 2 minus 1 in the numerator, 1 minus, now multiply this out. It's going to be this squared is 2. You can get minus 2 root 2 with a minus sign, so it's going to be plus 2 root 2, and then plus a 1 with a minus sign, so it's minus 1. So that is 1 minus 1, they cancel, and we get 2 root 2 minus 2. So it's 2 over root 2 minus 1, and 2 root 2 minus 2. You could factorize the 2 out, but you can quickly see that that is 1, which is what we expect, because it's what we effectively already knew. And again, maybe they didn't intend us to do it this way because we've run out of room. So yeah, basically let's do the same thing again, risking using up space for the next question. So tan 3 pi over 8 is going to be equal to tan pi over 4, 2 pi over 8, pi over 4, plus pi over 8, and that's equal to tan pi over 4 plus tan pi over 8 over 1 minus tan pi over 4 times tan pi over 8, and that's tan pi over 4 is 1 minus, plus, sorry, that's a plus on the top. That's what happens when you're working and use bad handwriting. You can't read it when you get to the next line. So tan pi over 8 we're told is root 2 minus 1, and in the denominator we've got 1 minus tan pi over 4 is 1 times root 2 minus 1. That's the ones cancel in the numerator, so we've got root 2 on the top. We've got 1 minus 1, so 1 plus 1, so that's 2, and minus root 2. As standard practice, we rationalize the denominator by multiplying by 2 plus root 2 over 2 plus root 2. That gives us 2 root 2, and root 2 times root 2 is 2, so that's 2 plus 2 root 2, and 2 times 2 is 4, minus root 2 times root 2 is 2, so that's going to be 2, so we're going to get 1 plus root 2 for the tangent of 3 pi over 8. So we've got root 2 minus 1, and we've got root 2 plus 1. That's our final answer to that part. And then it says, hence or otherwise, find all real solutions of the following systems of equations in exact form. So, this second one, that's got the tangent of two angles that are added together, so we could use the same rule to expand that out, and we get tan x over 2 plus tan y is 1 minus tan x over 2 times tan y. And that will give us tan x, I'll write it as a fraction, x over 2 plus tan y over 1 minus, and we notice that tan x over 2 times tan y, that's what we've got in the first equation, so we can rewrite that as root 2 minus 1. So 1 minus 1, that's going to be 2 plus root 2, so tan x over 2, and you'll notice I'm learning and I'm writing across the page, not spreading it out, anticipating I might run out of room. That's 2 minus root 2. And the question says this is equal to root 2 minus 1. So that we can rearrange this as tan x over 2 plus tan y is equal to 2 minus root 2 times root 2 minus 1, which is 2 root 2 minus 2 minus 2 times minus root 2 times root 2, which is minus another 2, and then plus root 2. I'm kind of getting that wrong, I think. I wrote the wrong thing in here. This is 1 plus root 2. This is 1 plus root 2. 1 plus root 2. So we get 2 root 2 plus 2. minus 2, and then minus root 2 here. So all of that is equal to, the 2's cancel, 2 root 2 minus root 2 is root 2. So this here is the, tried to change color and failed. This is the sum of these two tangents, and this one here is the product. That's exactly the sort of two expressions that we need for a quadratic equation. A quadratic equation, the c term, the constant term, is the product of two numbers, the two roots, and the b term is the negative of the sum of the two roots. So we could, let's say, write out a quadratic equation. We've got x's and y's, so we use w squared minus the sum of the roots, the sum of the two things we're trying to find is root 2, and plus the product is root 2 minus 1. So our two things, tan x over 2 and tan y, have to satisfy this quadratic equation. So quadratic equation, w squared minus aw plus, or bw, let's make it, bw plus c. B is the sum of the roots, and c is the product of the roots. So when we've got a sum and we've got a product, we can form a quadratic equation. Sum of the same two things as we've got the product of. And we can factorize this. So w, we want to multiply to get root 2 minus 1. So I think it's probably best, we want to add to minus root 2. So it's probably something, I think one of these is going to be a 1. 1 times what? It'll be minus root 2 plus 1. Does that work? 1w minus 1w and minus root 2. Yep, yeah, that works. So this will be our factorization. I just moved everything, so you won't be able to see me, so I need to move back. And this says that w equals root 2 minus 1, or w equals 1. I haven't actually used the thing that we had to find in the first part, so it says hence. I'm using what they give us in the first part, but not what we had to find, root 2 plus 1. So this says w is this, or w is 1, so we can take our two tangent equations. We need one root, tan x over 2 has to equal root 2 minus 1, which we were told is the tangent of pi over 8. And that means that these two angles have to be the same, or for tangents, they differ by a multiple of pi. Tangent graph just goes like this, and this is pi, so it repeats every pi. So we add on some arbitrary multiple of pi, that could be the same as well. So that tells us x is equal to, multiply by 2, pi over 4 plus 2k pi. So 45 degrees plus multiples of 2 pi. And if tan x over 2 is equal to this, then we would simultaneously have tan y is equal to 1. So that means y is equal to pi over 4. That's right of 4. Plus the same. Let's change that to a different variable. It's plus n pi. So this is one solution. The other solution that you could have is tan x over 2 was equal to the 1. So that means x over 2 is equal to pi over 4 plus, let's be inconsistent and say m pi. So this is x equals pi over 2 plus 2m pi. And we would have tan y is equal to root 2 minus 1, which is tan pi over 8. So the y is equal to pi over 8 plus n pi. So these two solutions go together. And I think that's us done. Part C. A local council wishes to supply internet to an island 30 kilometres from the mainland. One option involves running a cable between point A on the island and point B on the mainland, 40 kilometres further down the coast as shown below. The cost to run a submarine cable under the water is $W per kilometre, and the cost to run an underground cable on the mainland is L per kilometre. L for land, W for water, where W is greater than L, so it costs more to run the cable under the water. So the shortest distance, obviously, between 2 points is the straight line. That's a well-known statement for our normal sort of geometry. But because it costs more under the water, it could be better to go, well, it will be better to go some distance down here before we go up here. Well, it will be better depending on the costs, actually, because sometimes the costs won't, the benefit from going straight down won't compensate for the benefit of going straight across, or benefit of going down. The extra cost of going further in distance won't compensate for the reduction in distance we have to go under the land, as we will see later. So this sort of question, it helps to put some basic coordinates on here, and it doesn't really matter where you put the coordinates, you just have to be consistent. I did for this one, I put my x here, and I made this 0, so x was this distance out from here to some point where I am going to start putting the cable under the water. That means on this hypotenuse we're going to get a distance of the square root of 30 squared, which is 900 plus x squared. And x is going to tell us the distance from the point opposite point A on the mainland. I've seen someone else do the same question and they put an x over here, and then you get a 40 minus x. You'll get some different algebra you have to do, but the question will still solve that way. Now we need to look at the cost. They've used W and L for water and land, so let's use C for cost. It is helpful when you're reading these things back to use variables that make some sense. We need to formulate a cost equation. Well, the cost is how much it costs to do the cable on the land. So here our cable is going to go along here and then along here, along the hypotenuse. So we have a distance of 40 minus x along the land. So that will be multiplied by the cost of the land. And then we've got plus our hypotenuse, 900 plus x squared, times the cost of putting a cable in the water. L and W are just constants. We can just leave them there like they are. We've got some relationship between them which we will use later, but there's no need to do that at this stage. We want to minimize this cost. Minimize the cost. That says use algebra. So if we go dc by dx and we differentiate this, when we differentiate this bit here, we just get minus L. It's just a 40L as a constant that vanishes, and minus L times x, we get minus L. And when we differentiate this bit, it's a chain rule. This is to a power of a half, so you get a half. This to the power of minus half, which is basically 1 over the square root. And then multiply by what the derivative inside, which is 2x. And we've got this constant as well. So that's not too tricky, and we want to get a minimum, so we want to set this derivative to 0. I think the simplest way is to shift the constant over to the other side, so we get, we've got a cancellation of the 2's in the numerator and denominator first, so we're going to get x over the root of 900 plus x squared is equal to L, shifted over the other side. I'm going to divide by the W. And just to save a bit of writing, I'm going to call this L over W equal to K. And we can see down here, if you do that, if you go L over W, that's L over like 1.5 L in the first case, and the L's cancel, so you actually get 1 over 1.5. And that's what I've just called K. And in the second example, it'll be 1 over 1.2. But we don't need to worry about writing all that down. We'll just call it K for now. And we've got to solve this. So we've got a square root. The way to solve these sort of things is to square everything. So you get x squared. Let's write that up here. We're going to get k squared and 900 plus x squared. So I got rid of the square root and multiplied it up on the other side. And we just get an x squared here. We get x squared. If I take off the k squared x squared term, we're going to get x squared over here, and then 1 minus k squared is equal to 900 k squared. So we get x equals, or x squared equals, well, we can do x actually. X equals, we're shifting all this over, and we're taking a square root. So square root of 900 is 30. Square root of k is k. That's okay here because k is always positive. And the square root of 1 minus k squared. You can do more lines of working if you need to. And this tells us the value that we want for our x here. Let's put in our values of k. So k equals 1 over 1.5. What happens? We get x is 30 times 1 over 1.5 over the root of 1 minus 1 over 1.5 squared. You can just do that however you want with calculator. I have done the calculation. And I get 26.8 kilometers. So that says where W equals 1.5 L, that we want to go 26.8 kilometers from this point. That'd be 13.2 kilometers from B. And that's the point where we start going under the water. So 13.2 kilometers on land, and then across the water. The question asked us use calculus to determine how the cable should be installed. So 13.2 kilometers from B or 26.8 kilometers from a point on the land opposite A would determine this point, and that tells you where to go or how to do this to get a minimum. We haven't actually determined that it's a minimum yet. I'll address that in a minute. When it's 1.2, you get exactly the same sort of calculation. Square root of 1 minus 1 over 1.2 squared. In my notes I haven't actually got that written out, but you get a value here that is bigger than 40. And bigger than 40 is a problem because that means we're out here somewhere. So it's saying the minimum cost is to go this way and then go along under the sea. Well, that can't clearly be the case. We didn't write it out, but implicit in our cost formula was that x lay between 0 and 40. Because if we go out this way, that would mean that this part of the formula, 40 minus something, it would give us a negative cost for going back this way. And that's clearly not the case. So what's happening here is the mathematical formula without that condition on that x had to be less than 40, it was contributing a negative cost by going in the opposite direction. So when this is the case, that means lowest cost is to go directly under the water. Don't go anywhere along the land. And up to this point, we've been assuming that we've got the lowest cost here. We do need, for this question, to show that we've got a minimum, and the way we show we've got a minimum is find a second, or one way to show is to find a second derivative. So we could find d2c by dx squared. Look back at our derivative, we've got this expression here. The L term is going to cancel, and then this bit has got xw over root 900 plus x squared. Might actually help. Let's write it all out. This is what we're working with. dc dx we had found was minus L plus xw over the root of 900 minus x squared, or plus x squared. Plus x squared, double check. Yeah, 900 plus x squared. So if we want to find the second derivative, d2c by dx squared, we get nothing from here. This is a quotient. The quotient rule says write down what's on the bottom, multiply by the derivative of what's on the top. subtract, write down what's on the top, and multiply by the derivative of what's on the bottom. We did one like this just before up in the question. So the derivative of root 900 plus x squared is a half 1 over the root 900 plus x squared, and then multiply by 2x. The 2's cancel, and all of this is over the denominator squared. That's just getting rid of the square root. This looks messy, but we can get quite a bit of simplification. So we've got a fraction here in the denominator. If we multiply the whole thing by root of 900 plus x squared over the root of 900 plus x squared, that will get rid of this fraction in the denominator. So we will have, when we multiply it by the root of 900 plus x squared, we just lose the square root part there, and here it cancels, so we get minus x squared w, x times w, and on the bottom we get 900 plus x squared times the square root of 900 plus x squared. And there's a simplification that we can see. We've got x squared w here minus x squared w, so this term cancels with all of this. And what we're left with then is 900 times w, 900 plus x squared on the bottom, and the square root of 900 plus x squared. We can put our values in for x squared and work out what this is, but we don't need those values. All we need to know is that this is bigger than 0. This is 900w is positive. 900 plus a square will be positive. 900 plus a square will be positive. Take the square root, we'll get a positive. We've got three bits that are all positive. We have to be positive, and once we know that we've got a positive, therefore we have local minimum. So we've found that we've got a local minimum here, and we've got a local minimum for some value x bigger than 40, which means that the best we can do is actually go direct underwater. And this question gave us a whole lot of extra space which we didn't use, or maybe I used it by going down the side, but we have completed question 3. So any questions in the comments? Otherwise, I'll see you next time for question 4.